Hello everyone, welcome to my YouTube channel. Today we are going to discuss um, is there a serious fundamental flaw in our understanding of time? But before that, I am Rohit. I am the author of this book, Decoding Gravity, Time and Causality. This book is basically going to come internationally soon. So it is describing dynamic general relativity, a new theory of quantum gravity and a potential theory of everything. So I think it is a big thing which is going to which is going to come in physics. So I recommend that you buy this book. But anyhow, this is the YouTube channel in which I am going to keep giving some secrets of what is the theory and all that. So I recommend that you subscribe to this channel and also share if you like it. So we'll come to the problem of time. Now, before that, realize one thing, that whatever I am discussing over here is my beliefs basically. So it's not accepted science yet. So what we are going to ask are some questions which general relativity is unable to answer, or rather, contemporary physics is not able to answer. So what is time? I'm not going to go into detail of what is time and why it is important and why it is not. We know that time is basically, there's an arrow of time, and the second hand of a clock, it keeps ticking and it goes forward. It keeps, why does it not go backwards? But these are not relevant here. What is more relevant is in physics, um, time is an enigma. We don't know what exactly is time. So what is quantum mechanics in time? Basically, in quantum mechanics, time is absolute. That is, there is only one background entity of time. But in special relativity, if a clock is moving, it ticks slowly. What about general relativity? In general relativity, again, if a clock is nearer to a gravitationally active object like the Earth, then it stops. It reduces. It ticks slower. So there's a gravitational time dilation, velocity time dilation, and gravitational time dilation. So the time is a bit different. So what about LQG? In LQG, there is no time actually. So the time disappears. So these are multiple theories which we have, and they have different measure of time. So we don't know what exactly, which of these is right, which of these is wrong. And so basically, I think that we have a bit of flaw in understanding of time. Anyhow, what we'll just stick to general relativity here. So pardon this image actually, but this, just imagine that this is a skyscraper and this is the Earth. And general relativity says that because of the gravitation of the Earth, these are basically time zones which I have drawn actually. So gravitational time dilation happens, and so there are, you can imagine time zones where gravitational time dilation is equivalent. So time here is running much slower as compared to here, and as compared to here. So 1 second here is much it's a slower 1 second as compared to 1 second here, and 1 second of here is much smaller. It's much the clock is ticking much faster here. The clock is ticking much faster here. So anyhow, imagine that there is this distant observer, and this distant observer is basically observing this building. Imagine that this building is having blue color, and the frequency of is basically x per seconds. Okay, so when the light rays are starting from this building and they're going here, the frequency is x per second. But we have to realize that 1 second is it's much more dilated here as compared to here. So what exactly is this? Is there a when the so we don't know basically. So this we don't know whether to consider waves wave nature of light or particle nature of light. But anyhow, so the frequency of waves starting from here, x per second. But what exactly is this per second? Is this because here a second is much more dilated than here. So what I mean to say is that the rays which are starting from here and rays which are starting from here and the rays which are starting from here will have a different frequency basically, because 1 second is much more dilated over here as compared to 1 second here, and 1 second is much less dilated here. So the distance, so you have to realize that the distance is the same all throughout, but the distance is same throughout, but time is dilated. Let me tell you that this is not entirely right, because distance is also not same all throughout, because the distance here, all the space is contracting as per general relativity. We'll come to that. So the question which I would want an answer to, which I don't have, if any of you have answer to this question, you can write in the comments. I would be glad if someone answers the question. But so if this I know that the difference would be very, very less, but is it that the blue color which comes from here is different than the blue color which comes from here? Because the waves which are starting, the 1 second here is different than 1 second here. So the number of waves which arrive in the eye of this guy will be of different color, because there will be more. So the frequency here will be much less than the frequency here. So you can say that there is a difference in blue color. Imagine that this is a person. This is not on Earth. This is basically a much massive planet near the supermassive black hole of the center of the Milky Way. So all the gravitational effects are much more pronounced as compared to the Earth. So do you think that the blue over here will be different than the blue over here, because the waves which are starting are basically different, are of different frequency as compared to here, because of the time dilation over here. Anyhow, I would also want to give a small hint here, that imagine that this is a Planck clock, and imagine that this sphere is a photon. Imagine that so we know that this photon, imagine that this photon is moving from left to right. So we know that this photon is basically it has to move 1 Planck length in 1 Planck time. Okay, so imagine that these are tiles, and these are 1 Planck length in dimension. So this photon has to basically hop every tick of the Planck clock, this photon will jump from here to here. Again, one tick of Planck time, it will jump from here to here. Now imagine that these whole tiles are arranged on a miniature treadmill, and this treadmill we can start and stop whenever we want. So if the photon jumps one Planck length in one Planck time, but the treadmill is moving in the opposite direction with the speed of a half Planck length in one Planck time. So basically, the photon will jump here, but the location of this tile will be shifted a half Planck length over here. So basically, what I'm trying to say is that the photon is moving forward. So it's basically, so what is special relativity saying? Special relativity is basically based on Maxwell's equation, which says that the speed of light is basically dependent on the vacuum permittivity, and so all the two constants are basically constants which are dependent on the properties of the vacuum. So they are basically independent of the velocity of the source. So if the source is moving, whatever velocity it might be moving, but the speed of light has to remain constant. So this particular photon is basically honoring special relativity. But even then, because of this treadmill, it cannot move forward. Whenever it's moving one Planck length in the forward direction, it is being pulled back by about half Planck length in the opposite direction. Now, what if the treadmill is in fact faster? What if the treadmill is moving backwards 2 Planck lengths in one Planck time? So what is maybe one Planck length in one Planck time? So what will happen is that in one Planck time, this will jump here, but the location of this particular tile will shift one Planck length here, which means that the photon, any forward progression of the photon basically is completely negated by one Planck length regression of the treadmill, which means what? The photon will remain here. It will stay here. It cannot move in front. So what if it is faster? So the photon will try to move here, but it will move here. It will try to move here, but it will move here. So it will get sucked inside. What if the treadmill is in the opposite direction? If the treadmill is moving along the direction of movement of the photon, so photon will move one Planck length in one Planck time, but the treadmill will also move one Planck length in one Planck time. So the photon will effectively move 2 Planck lengths. So because photon will jump into this tile, but the treadmill will basically shift the location of this tile here, which means that the photon is effectively moved 2 Planck lengths in one Planck time, which means that the velocity of the time has increased. Basically, the velocity of the photon has increased. Basically, it's become twice as much as the speed of light. So what exactly are we talking about? Basically, this treadmill is basically, what I'm saying is, what if the nature has rigged the system, and the nature has made this particular treadmill like rigging of the system, so that the photon can be pushed or pulled, so that so if this kind of a rigging is there is, what if there is an active spatial contraction? Now, general relativity itself says that there is an active spatial contraction, not exactly active, But general relativity says that, you know, space can contract and time can dilate, and space can. So this spatial contraction is a part of general relativity. So what if there is an active spatial contraction over here, and this photon is basically being pulled behind, so that it is moving in front, but it's not able to move in front with the same velocity. So it is basically this active spatial contraction. What will it do is that it will change the velocity of the photon, or basically variable speed of light. So general relativity is not actually completely against variable speed of light, and it is not. It is honoring special relativity. So it's not violating special relativity. So a variable speed of light is not completely violating special relativity as well. So presently, our understanding of general relativity does not say a variable speed of light theory. But Einstein himself had published a paper in 1911 which suggested a variable speed of light theory. But he did not understand the significance of it actually. He had actually solved the whole problem in 1911 itself, but unfortunately nobody gave that much attention to this particular paper. So anyhow, you can also imagine this particular circle to be, imagine that this is not a photon clock. Basically, this is, imagine that this is an atomic clock, and this is a cesium atom, and it's basically vibrating. And the same arguments, or same setup, or same arguments can be made about the photon, the atomic clock as well. So if there is an active spatial contraction over here, and if there is a treadmill-like thing, so if the photon, if this particular atomic clock is basically vibrating, and when it is moving towards the center, there is an active contraction over here. The treadmill starts and it pulls the atomic clock, so that the vibration of the atomic clock reduces. So if the rigging is much more near the surface of the Earth, the atomic clock will vibrate much slower nearer the surface of the Earth. And as we go away, the vibration, the rigging is much less there. So the hindrance to the movement of the vibration of the atomic clock is much less. So you will detect a much lesser gravitational time dilation, or the vibration of the photon clock will increase, the atomic clock will increase, which means that your atomic clock will measure a much lesser gravitational time dilation. Now, these are all arguments, basically. We don't know for sure. I hope that I know that whether this is right or wrong is we don't know yet, and we have to. Physicists have to review my book, and all these things are given in the book. You have to review the book. So I suggest that if you know, if you think that the arguments which I've presented in this are right, I suggest that you go through the book, go through all the arguments of the book. It is very difficult to give all the arguments in this small YouTube video, but I've tried. Thank you very much for your attention. Thank you.